Be sure to check out the 3D versions of this video at the links in the video description.
Okay, let's talk about the moon. Here it is over here. Let me bring it over here in front of you. So what we're looking at here is the far side of the moon. This is always the far side. The moon is tidally locked to the Earth. So when you're on the ground looking up, you're always looking at the near side with all the dark splotchy areas on the moon. So let me turn it around here and back it up a bit. Alright, so you see all the dark splotchy areas. These are known as the lunar maria. Each one is called a mare, or sea in Latin. And they're called seas because long ago astronomers thought they were actually bodies of some kind of liquid. But in fact they're these large low-lying areas that are the result of early volcanism. And they tend to appear much darker than the rest of the moon because they're iron-rich basaltic material. And basalts tend to be dark and gray. And so all of these dark splotchy areas are named seas, except for this one over here, the big one on the left. This is named as an ocean, Oceanus Procularum, Ocean of Storms. It's a very pretty name. Now there are other smaller basaltic plains named as bays and lakes and so on. Now the moon is a bit more interesting than what it's made of because it's the only place other than Earth that humans have been to. The space race between USA and the Soviet Union is a fascinating part of human history if you look at all the activity that went on starting in the late 1950s. I only have time to touch upon a small part of this activity here, and I'll show you where some of the major milestones took place. The Soviet Union Space Agency had a program called Luna. So they would just send out mission after mission, all under this Luna program. By contrast, the American Space Agency, NASA, employed several different programs, all with their own objectives, such as Ranger, Surveyor, Lunar Orbiter, Mercury, Gemini, and Apollo. In 1959, Luna 2, right here, impacted right here on the surface. And by impact I mean it was a hard landing. And that became the first human spacecraft to reach the surface. Later that year, Luna 3 didn't land, but it got the first images from the far side of the moon. And that was quite something, to realize that the other side of the moon that we had never seen before at that point was all of this heavily cratered highlands with just a couple of those little dark sea areas, totally different than what we normally see. 5 years later, in 1964, NASA sent over Ranger 7, which impacted right here. And that became the first American spacecraft to reach the surface. In 1966, a bunch of milestones happened in rapid succession that highlight just how close this race was. The Soviet Luna 9 became the first ever human spacecraft to successfully soft land on the moon. That was right here, on the edge of the ocean. So it soft landed without breaking apart, and it sent back awesome stereo 3D circular panoramas of the surface, which is amazing for the time. Later that year, Surveyor 1 became the first American spacecraft to soft land on the surface. Also later that year, the Soviet Union's Luna 10 became the first spacecraft to successfully orbit. And guess what? It's still there today, in orbit. Luna 10 is the craft that discovered that there are these uneven concentrations of mass under the surface, informally known as mascons. And it's important to know about these because their gravity affects the trajectory of lunar missions, of anything flying closely over the surface. So later that year, what do you think Americans managed to pull off? You guessed it, Lunar Orbiter 1 became the first American craft to successfully orbit, again right after the Soviets. In 1968, NASA's Apollo program was heating up. This is the program that would use everything they had learned up to that point to send humans to the moon. Apollo 8 was the first crewed mission with actual people on it, and that managed to do 10 orbits around the moon before returning home to Earth. What an amazing ride that must have been. And if we're lucky, we'll start seeing that sort of trip happen again in the near future. In the following year, we have the famous Apollo 11 mission. Way over here at the bottom of the Sea of Tranquility. This is where the first humans were able to land and set foot on the moon. The astronauts on the ground there nicknamed the landing site Tranquility Base, named after the sea that they landed in. And that was the first time Americans managed to achieve a significant lunar exploration milestone before the Russians did. A year later, the Soviet Luna 17 landed right up here in the Sea of Rains, right here. And that became the first mission to deliver a rover to the surface of another solar system body. And that rover's name was Lunokhod 1, which was an 8-wheeled rover whose name meant Moonwalker. And it ended up roving around for nearly a year after landing. After that, Apollo 15 landed next to Mons Hadley and delivered its own rover, which was really the lunar buggy that astronauts could drive around for miles and miles around the surface. That Soviet rover was remote controlled, of course. In 1972, the final Apollo mission landed right over here, Apollo 17, in the Taurus-Littrow Valley. And that was the last time humans set foot on the moon, at least for now. And then the final Luna mission, Luna 24, touched down right here, and it was a sample return, so it brought back a little bit of lunar regolith, or soil, back to the Earth. So that was 1976. It was quite a dry spell after that, in terms of craft actually reaching the surface with some sort of soft landing, or any kind of landing. And it wasn't until 30 years later, in 2006, that somebody sent a craft to the surface called Smart 1. And who sent it? ESA, the European Space Agency. And that was the first time somebody other than the USA or Soviet Union did something with the lunar surface. Not long after that, in 2008, somebody else sent a craft to the lunar surface called the Moon Impact Probe. And who sent that? The Indian space program, ISRO. This probe smashed into a crater at the south pole of the moon called Shackleton Crater, and that is where it discovered water on the moon. In 2013, China's space agency sent and landed Chang'e 3 right up here, returning beautiful high-definition photos of the surface. And the lander served as the first telescope on the moon, as well as putting a rover on the surface named U2. At the beginning of 2019, Chang'e 4 pulled off the first soft landing on the far side of the moon, complete with another rover, another space telescope shielded from the bright Earth shine. So several other space programs are sending rovers to the moon in the very near future, so definitely watch that space. Humanity's expeditions into space are certainly maturing bit by bit, and this is aided by intense computerization and a growing impatience to get back out there. And I don't know about you, but I love the fact that there are now multiple capable space programs around the globe that are doing their work for the sake of exploration and science, without being so focused on winning a race. So let's look forward to a lot of exciting developments on the moon soon. Alright, let's wrap it up here. One more stop here at the Earth and the Moon, and then we take off for Mercury. Alright, so this tour stop will be a little different. Instead of talking about the Earth or the Moon, I'm going to quickly point out a few of the new features that are now available to you using your dashboard. If you're already familiar with everything here, then feel free to just skip past this. Just go ahead and go to Mercury and I will meet you there. Alright, so first up is the yellow button with the letter I on your left. That brings up more information for whichever tour stop you're at. It cycles through additional pages of text as well as real photos. There are page numbers shown above that button, which gives you a sense of how much there is to look at for that tour stop. Below that yellow button is a button that looks like it has stars on it. That takes you back to the tour map at any time. You can use that map to jump straight to any tour stop that you've already visited. Further to your left is a light blue button that activates a side-by-side comparison mode. So for example, right now you're able to see the Earth and the Moon next to each other, which makes it very easy to compare their sizes. With this feature, you can basically arrange any two solar system bodies next to each other to satisfy any size-related curiosity you may have. Over here on your right are a pair of small green and red buttons. Those are the options and help menus, respectively. And then over there, all the way to your right, is a gray button with a 0G on it. That activates the zero gravity EVA mode, where you can get out of your seat and float around here using your thrusters, or just to grab onto planets, moons, or your frame here, and so on. You'll definitely want to look at your controllers to see how to move around in 0G. For example, if you start falling toward the sun, you want to know how to brake and how to come back to the cockpit. When you get close to a planet or moon in 0G mode, you'll be able to see surface labels for most of the interesting features, as well as points of interest where various spacecraft have landed or crash landed. You'll have the ability to toggle these on and off, for example, if you wanted to quiz yourself, or if you just wanted to see the planet in its naked state. The only planets that don't have labels are Earth and the major outer planets. For Earth, well, you can just refer to your favorite mapping software. And for the outer planets, they're clouds and gas. There's no surface, and for the most part, nothing stays still long enough to be labeled. That's all for now. Whenever you're ready, let's head out to Mercury and journey through the rest of our beautiful solar system. This thing looks like the moon. Definitely bigger than the moon, though. It looks like a moon that has none of those dark lava plains. It does have a few, but as a rule, they simply aren't darker than the rest of the planet. And like the moon, it also sports a few prominent ray systems. What's a ray system? Well, let's look for one. Alright, here's one. You have a little crater with a bunch of obvious streaks coming out of it. When a big rock slams into the surface of any body, that rock doesn't just make a dent and push surface material out of the way. It literally explodes as it embeds itself into the surface. All that kinetic energy has to go somewhere. Most of the time you get a smooth blanket of material that settles around the crater, an ejecta blanket. But sometimes the impact energy is unevenly distributed and creates a bunch of long streaks, known as a ray system. There are more than 30 of these ray systems on the moon, but only a handful here, although they are very prominent here. Despite being the smallest major planet, Mercury is home to one of the largest impact basins in the solar system, the Caloris Basin. I'll try to trace a rough circle around it here. This big section right here. It can be difficult to make out because, again, the lava plains are basically the same brightness as the rest of the planet. It is surrounded by a ring of 2-kilometer high mountains, so when the sun isn't overhead, you can make out the shadows of the ring. What we can do right now, though, is enhance the colors a bit to make it more obvious. Aha! There's your Caloric impact basin. Super obvious now. So what is this map? NASA's Messenger spacecraft was able to provide data for this false color map by measuring the spectral composition of every part of the surface. And these colors simply highlight differences in that composition, differences in what it's made of. Mercury is the least tilted planet in our solar system with respect to the orbit around the Sun. This is in stark contrast to Earth's 23-degree tilt. Therefore, Mercury doesn't have seasons. Although, it kind of does, because if you were to live in a house right here on the night side, you'll be freezing for about 3 months, and then cooking in the sun for another 3 months. Why? Because while Mercury has the distinction of having the shortest year, the length of its day is very, very long. A Mercurian year is a mere 3 Earth months. It's very short. Just has to go in a tiny little circuit around the sun. But the planet itself rotates very slowly. It takes over 2 Earth months for Mercury to make one complete rotation around its axis, which is 2/3 of its entire year. This is known as a 3-to-2 spin-orbit resonance, which is stable and locked in because of Mercury's elliptical orbit around the Sun. Now, normally the length of a planet's rotation gives you an indication of how long its solar day is. Not so here, because it's rotating slowly yet quickly going around the Sun at the same time. So what we think of as a day, where we're on the surface watching the sunrise and the sunset and having the whole day-night cycle, is even longer at 6 Earth months, exactly twice the length of its year. Very strange. Another side effect of its low tilt is that there is also a lot of water ice in the permanently shadowed craters at the poles, just like on our moon. Being small, Mercury's outer layer, the crust, quickly cooled down and hardened into what we think of as rocks. And then later, as the inside of the planet cooled down, the entire planet shrunk a bit, causing that stiff crust to wrinkle up and form scarps, which are these linear features that are basically huge cliffs, with some reaching 3 kilometers high and running for hundreds of kilometers. In Latin, these are called rupes, so if you see those on a map, you'll know what those are referring to. As with most solar system bodies, there is an official naming convention in place here. Plains are named after Mercury in different languages. Mountains are named for the word hot in a variety of languages. Craters are named after great figures of the arts, and rupes and scarps are named after famous ships of discovery, and so on. But getting back to what's inside the planet, Mercury is known as an iron planet, unlike the other inner solar system planets. This is because Mercury's iron core is huge compared to the other rocky planets, occupying a whopping 3/4 of its diameter. Why? Why is this? The most popular explanation for the size of this core is the giant impact hypothesis, whereby the impact that made the Caloric basin was somehow responsible for remaking Mercury by violently shaking off the outer layers of the planet. However, findings from the recent Messenger orbiter mission actually favor another hypothesis, whereby the spinning solar nebula surrounding our sun in the early solar system reached all the way out here to Proto-Mercury's orbit and was able to prevent lighter material from sticking to the planet as it formed. There is another spacecraft on the way named Bepi Colombo that aims to shed some light on why Mercury's iron core is so large, and to narrow down our ideas on why Mercury's early formation. Bepi Colombo is a joint mission between ESA and JAXA, the European and Japanese space agencies, and it is due to begin orbiting Mercury in 2025, where it will detach into two separate probes doing different things in orbit. It's actually quite a feat to orbit Mercury. The only spacecraft to visit Mercury before Messenger was NASA's Mariner 10, which did not orbit, but instead made 3 flybys of Mercury while orbiting the Sun. And it is still orbiting the Sun today as a dead and heavily irradiated spacecraft. But to orbit the planet itself requires slowing way down after launching from Earth. Wait a minute, slowing down? Isn't Earth already moving slower than Mercury? Well, yes, Mercury is traveling through space much faster than Earth due to its smaller orbit. But any spacecraft launching from Earth actually has to slow way down in order to fall toward the Sun and into Mercury's orbit. And by the time you fall into that smaller orbit, you end up traveling faster again. It requires a lot of energy to slow down that much. And for Mercury, we generally accomplish that by carefully using multiple gravity assists from other planets to drastically change the trajectory and speed in creative ways. Now, let's drastically change our position and go check out Venus. Here we have Venus, named for the Roman goddess of love. Venus is always the brightest planet as viewed from Earth, and as such holds a prominent place in the lore of many cultures. It's very easy to see in the sky. Then, when the telescope came along and we realized that Venus was actually a mysterious place rather than just a mysterious point of light, fantasies about alien life on Venus were common in the public consciousness from the 1930s to the 1950s. In some ways, this is our sister planet. It has nearly the same size and density and overall chemical composition as Earth, and it is the planet that can come closest to us as it travels through a nearly perfectly circular orbit. And that's where the likeness ends. Venus is completely covered in sulfuric acid clouds and a thick carbon dioxide atmosphere. It's so thick that only large meteors can make it to the surface and form a crater. It's so opaque that you can't see the surface from the outside. You can't even see the sun from the surface. It's dark down there. And standing on the surface would be like feeling the pressure of swimming 1 kilometer underwater on Earth. That surface pressure is high enough that you would be standing in supercritical carbon dioxide, which is a weird state where it behaves like both a gas and a liquid at the same time. Venus and Mercury could not be more different, but they do share something in common. Venus rotates slowly, just like Mercury. Venus has the slowest rotation of any planet in our solar system, and is slow enough to be a perfect sphere, like Mercury. And because of this slow rotation, its day is longer than its year, although not nearly as long as Mercury's. One of the most striking discoveries about Venus is that it has the same temperature all over the planet, no matter if it's the day side or night side, pole or equator. A scorching 470 degrees Celsius surface temperature, or nearly 900 degrees Fahrenheit. Venus is not the closest planet to our Sun, yet it is by far the hottest planet in our solar system. The Venusian atmosphere is extremely fast. It has extremely fast winds at high altitudes, and because of its high pressure atmosphere, it has very slow and yet very strong winds at the surface. Overall, the atmosphere rotates up to 60 times faster than the planet itself. What do you think happens over a long time with an atmosphere like that? The atmosphere effectively pushes on the planet's surface and thus tries to speed it up in the direction of those winds. And this is one reason why Venus rotates so slowly. The atmosphere and the sun both work together over time to slow it down. And then once the rotation came to a stop, the winds kept pushing. So now the planet spins backwards compared to most other solar system bodies. The sun's gravity is still a factor here, and it keeps Venus from spinning too fast in the other direction. So this is all you can see from the outside. What's under all that? This is a radar map made using data from NASA's Magellan space probe, which mapped about 98% of the surface in the early 1990s. This map shows both elevation and reflectivity. The colors show elevation, so low elevations start with purple and work their way up through the greens and yellows and finally up to the high elevation reds. Bright areas are highly reflective and dark areas are not. It's obviously not what you would see if the clouds were stripped away. Nevertheless, it can help us visualize different landforms and put names to them. The bright white areas at the tops of some of the mountain ranges is indicative of a sort of metallic snow-like substance, but it's not yet known exactly what it's made of. If you were to look around at the names of these features, you'll see a lot of Latin terms, so it helps to know what some of these refer to. Mons is a mountain. Montes is plural, so it refers to a mountain range. Planum is a high plateau, while planitia is a low-lying plain. Fluctus is an area covered by a volcanic outflow. A corona is a large, roughly circular or oval-shaped feature produced by magma repeatedly pushing up from the mantle and falling back down under the crust. Got a bunch of coronas here. Here's one, here's another, and another, all over the place. So when that magma actually does spill out onto the surface in one big and slow eruption, it can form a flat feature 100 kilometers across, but less than a kilometer high. This is known as a pancake dome. And this is a feature unique to Venus, and they are commonly found near the larger corona features. So for any given corona, you may find a few pancake domes nearby. Another unique feature to Venus is the tessera. It refers to the very heavily deformed terrain that appears to look polygonal, or as if it were a mosaic of tiles, like right here. This giant section right here is a tessera. And these are thought to be the oldest parts of the surface. these unusual landform kind of makes me wonder what kind of strange features are unique to other planets, especially those outside of our solar system that we won't get to see for a while. By the way, all 2,000 surface features on Venus are named for females, from first names in different cultures to women of history to goddesses of myth. There are 3 exceptions to that rule: Alpha Regio, Beta Regio, and Maxwell Montes. Maxwell Montes is right here, and this is Venus's highest mountain range, with Scotty Mons being its highest peak. These mountains are named for James Clerk Maxwell, whose work predicted the existence of radio portion of the electromagnetic spectrum. And radio waves are how we're able to peer through the opaque clouds of Venus and see a map like this. So, you got mountains, ridges, faults, and folds all over the place here. Does that mean Venus has shifting tectonic plates like we do on Earth? No, that does not appear to be the case. All of these landforms are actually explained by the activity deep in the mantle pushing around the crust. On Venus, the separation between the crust and the mantle is far too sticky for the crust to be able to move around on its own. Early on, Venus likely had an Earth-like environment. It's very similar in size, density, and chemical composition, and it probably had a lot of liquid water. However, at one point the planet heated up enough to evaporate all of that water, which then locked the planet into a runaway greenhouse effect. And now the atmosphere is thick and made of 95% CO2, carbon dioxide, and plenty of water vapor. It's hard to believe that Venus ever had any chance at life, due to the fact that it does not have plate tectonics, and it currently has over 1,600 major volcanoes. That's a lot of volcanic activity. 160 of those volcanoes are considered to be bigger than 100 kilometers across. That's a lot of big planet-changing eruptions. On Earth, the big island of Hawaii is the only volcano complex of comparable size to one of the big Venusian volcanoes. And remember that we can only see the tip of the Hawaiian volcanoes. It extends all the way to the earth floor, to the ocean floor. But all of these volcanoes on Venus appear to be dead, with the possible exception of Venus's largest, Mat Mons. However, as far as we can tell, every few 100 million years, the mantle underneath the crust is reheated by the planet's core. And because there's no plate tectonics, there's not an easy way for Venus to blow off steam, so to speak. And therefore, temperatures continue to rise and rise until the crust weakens. And then suddenly the whole surface is basically covered in lava and completely recycled by volcanic processes until it cools down again. And then the cycle starts over. So, what have humans done with Venus so far? This planet has actually seen plenty of exploration already, with the majority done by the Soviet Union. There have been a whopping 40 mission attempts since 1961, from the Soviet Union, United States, Europe, and Japan. There were a lot of failures in those first 10 years of attempts, but mostly smooth sailing after that. There have been at least 10 successful flybys, at least 11 somewhat successful landings, 5 successful missions, specifically going to the atmosphere itself, and 8 successful orbiters. One of those orbiters is operational today, Japan's Akatsuki probe. otherwise known as the Venus Climate Orbiter. From the name, you can probably guess what it's studying. One of my favorite missions was probably the Pioneer Venus Multiprobe of 1978, which was one big craft that dropped off 4 separate probes at different locations around the planet to compare various measurements. One of those probes was bigger than the rest, and it opened up a parachute at an altitude of 67 kilometers, so high, and then it sailed all the way down while watching the cloud layers go by. In spite of these successes, getting a lander to stay alive long enough to be useful in the harsh Venusian conditions remains a big challenge. That's all the time I have for Venus. Let's head for Mars. Hello, and welcome to the red planet, Mars. This thing is half the size of Earth, but has the same amount of land area, most of which is covered in reddish iron oxide dust. A Martian day is nearly the same as Earth's, at 24 hours and 37 minutes. This should be very convenient for any humans that eventually live on Mars. Mars happens to be tilted a bit, just like Earth, so it effectively has seasons, although the seasons are much longer here because a year on Mars is twice as long. And due to the distance from the Sun, Mars is more inhospitable than Antarctica, but it is still the friendliest place that isn't Earth. It has extremely cold temperatures as low as minus 143 degrees Celsius, but in certain cases, temperatures can reach as high as 35 degrees or 95 degrees Fahrenheit. This is a very healthy overlap with temperatures that are familiar to us on Earth. On the whole, though, average temperatures on Mars are well below freezing. And there are lots of glaciers all around Mars, and they're all covered in a layer of dust, and they are protected by this dust. And based on what we now know, it is thought that the ice in all of the Martian glaciers is equivalent to what could cover the entire surface of Mars with 1.1 meters of ice. That's a lot. In addition to the glaciers, there is actually a lot of water ice in the soil. So if you were to dig 1 meter down, anywhere in the top or bottom third of the planet, maybe half of the material that you excavate will be water ice. So today, when the occasional crater is formed, it exposes ice to the air, and the ice stands out pretty easily, but it usually evaporates within months. Mars is named for the Roman god of war, which originally came from Greek mythology, where the god of war was named Ares. As such, sometimes you'll hear about Mars-related things as Martian or Aryan. But before I go into more detail about the planet itself, allow me to point out Mars's 2 very small moons, Phobos and Deimos. Phobos, the bigger of the 2, is a dark moon and is the closest moon to its planet out of any in the solar system. Its name comes from the Greek god of fear. Despite being a 27-kilometer wide rock, around 30% of Phobos' interior is hollow. And there is an unusual building-sized boulder sitting on its surface, informally known as the Phobos monolith. There's Phobos now. That monolith is 85 meters across and 90 meters tall, and it has been suggested as a landing site so that we can find out exactly what it is. The other moon, Deimos, is smaller and much smoother. That moon is named for the Greek god of dread and Terror. Both of these gods accompanied their father Ares into war, which is why you see them all together here. Both moons were discovered in 1877 by the astronomer Asaph Hall III, and he also determined the mass of Mars from the orbits of those two moons. The origins of the two moons, though, is still uncertain, with two main hypotheses being either an impact on Mars tossed up a bunch of rocks into orbit, which then coalesced into the oddly shaped porous moons, or these are captured asteroids, with the capture process being aided by a thicker atmosphere in Mars's distant past. If they are captured asteroids, the two moons may have been a binary asteroid that then separated over time due to tidal forces from Mars. And there are various observations that are consistent with one hypothesis and inconsistent with another, which is why this is still an uncertainty. Okay, so let's look back at the planet itself. Mars is a geologically impressive planet that sets many records. Let me turn this thing around so that we can see the big volcanoes. Here you have Olympus Mons, the tallest volcano in the solar system. It is 26 kilometers higher than the surrounding plains and basically just reaches into space. And if you were to drop it into France, it would fit just about perfectly. Then over here you have these three large volcanoes all lined up in a row. These are informally known as the Three Princes. They all sit on top of an elevated region called the Tharsis Bulge. This bulge is about 10 kilometers higher than the rest of the planet on average. This is an elevation map of Mars made by the Mars Global Surveyor spacecraft. Blues and greens are the low elevations, and the reds, browns, whites are the highs. As you can see, Tharsis is all red, and yet the rest of the planet is mostly green to orange. At the northern edge of Tharsis is Alba Patera. This volcano isn't that tall, but it covers the largest area of any volcano in the solar system. Then way down here, we have the deep Hellas Basin, the result of a large impact. It is 2,200 kilometers wide, and it is the largest visible impact crater in the solar system. And then if you look up here, you see this very large, smooth blue region at low elevations. This actually wraps around the entire northern hemisphere, and it is thought that a Pluto-sized body once collided with Mars at the top of it, although this is unconfirmed. However, a relatively small part of these plains, known as Utopia Planitia, right over here, is currently the largest confirmed impact basin in the solar system. So there is plenty more to say about Mars, but it will have to wait for the next tour stop. Okay, let's continue. So, Mars has been volcanically active for its entire history, though it is only the Elysium and Tharsis regions that have been active for the last 2.5 billion years. And they certainly look dead now, but there's no conclusive evidence that its volcanoes are now extinct. Mars's crust is too thick for plate tectonics, like what we have on Earth. And this is partly why volcanoes can get so large here. Volcanoes just sit there in one place over a source of magma, spilling out lava over and over again in the same spot. So they build up these huge mounds over time. The Tharsis Bulge is very heavy, and over time has caused lots of cracks to appear in the surface. Valles Marineris is the most obvious example of this. It is a system of cracks and chasms that happens to point toward the Tharsis Bulge. It is thought that as the Tharsis region thickened, Valles Marineris opened up as a crack and then grew very wide over time due to various types of erosion. And speaking of erosion, Mars may be old and dead compared to the Earth, but it still experiences processes today that reshape and erode the surface. Sure, you have the slow movement of glaciers carving out rock and causing valley walls to break apart, but there's also another process in play here that is very interesting. Allow me to walk you through it. Mars has these polar ice caps, mostly made of carbon dioxide or CO2. And usually one pole has more ice than the other and they will trade places every once in a while. There's plenty of water ice buried under the CO2 ice caps. In fact, there's enough to cover the whole planet under 11 meters of water. But the part that we can see is basically the CO2 ice. So the key here is that both the atmosphere and most of the polar ice caps are made of the same substance, CO2. That means that for half of every Martian year when polar ice grows, atmospheric pressure drops by quite a bit, as up to 25% of the entire atmosphere is turned into solid CO2 ice. This is known as atmospheric collapse. So then, when it comes time to melt, all of that CO2 sublimates straight from ice back to gas. After all, it's basically dry ice. And this sublimation creates a lot of interesting small-scale features, but it can also generate a lot of strong winds as the atmosphere quickly repopulates. In turn, those winds generate a lot of dust storms, and sometimes creates global dust storms that last for weeks, sometimes months. These storms can get really intense and even can obscure all of the big volcanoes from view. When we first put a spacecraft into orbit around Mars, there happened to be one such global dust storm in progress. As the dust subsided, these big volcanoes revealed themselves to us for the very first time. And that's what made the case for sending orbiters instead of relying only on flybys, just flying by once. So, dust storms erode the surface quite a bit. Since the atmosphere is thin, wind kicks around large particles that skip along the surface, eroding it and changing it over time. Now, unfortunately, Mars has lost at least half of its atmosphere over time to solar wind and especially to solar storms, where energetic particles emitted by the sun collide with the uppermost layer of Mars' atmosphere, knocking it away bit by bit. This was recently confirmed by NASA's MAVEN orbiter, and this was able to happen because of Mars' lack of a global magnetic field to shield the atmosphere, like what we've got on Earth. There is plenty of evidence for a lot of water on Mars' surface in the past. But unfortunately, today, water cannot stay in liquid form due to Mars' thinner atmosphere. In spite of its thinness, the atmosphere is still quite turbulent. Other than the winds, temperatures can change quickly. And in sunlit areas, there are sometimes large differences in temperature at the surface versus just 1 meter above the surface. These temperature gradients are one of the key ingredients to having weather, but without some sort of water cycle, there's usually no actual weather, just the seasonal dust storms and dust devils, the seasonal CO2 snow at the poles, visible frost around crater rims, and the occasional clouds. Speaking of clouds, Mars basically has two types. At very, very high altitudes, around 55 kilometers up, CO2 clouds can form. And secondly, you have water ice clouds that show up in different places. They appear at 22 kilometers altitude and tend to hang around the peaks of the large volcanoes. Water ice clouds also fill the deep Hellas basin with fog. And this sometimes makes the basin appear as a large bright spot when viewing the planet from far away. And then finally, once a year during the northern summer, a very large annular or donut-shaped water ice cloud appears around the North Pole. So, before we wrap up, I'd like to note some of humanity's efforts to explore Mars. Our first successful flyby was NASA's Mariner 4, way back in 1965. This is the mission that broke the spell of thinking that maybe the planet had Martians and artificial canals and things like that. In 1971, Mariner 9 became the first craft to successfully orbit another planet, and it returned over 7,000 images. Valles Marineris was named after that craft. Shortly thereafter, the first human-made object reached Mars' surface when the Soviet Mars 2 craft failed in its landing. Five years later, the Viking 1 lander made history with the first successful soft landing here at the Chrysae Planitia, and it returned the first color panoramas of the Mars surface. Today, Mars has a lot of company. 6 active orbiters, 1 or 2 active rovers, and 1 active lander. I say 1 or 2 rovers because one of them, Opportunity, is unfortunately not working after a recent dust storm covered up all of its solar panels. But NASA is still hoping to re-establish contact with it. Opportunity roved around the surface for an astonishing 14 years. And it is the one that discovered the hematite blueberries here in Meridiani Planum, right there. The other rover is Curiosity, here in Gale Crater. And it has been doing fantastic science. And then 600 kilometers north of that, NASA's InSight sits there listening for Mars quakes and to study the interior of the planet. Hopefully, in the next few years, we can take our exploration of Mars to the next level and put boots to the ground. It's a wonderful time to be alive. Wait, am I alive? See you at the next tour stop. So here we have Ceres. This is the first dwarf planet that we'll visit on our journey, and it is the largest asteroid in our solar system. Ceres is named for the Roman goddess of agriculture, and most of its surface features have names that are derived from the themes of harvests, fertile lands, and gods and spirits relating to such things. The symbol for Ceres looks like a scythe, like the kind you would use to cut your fields. The word cereal, the kind that you eat, is based on Ceres. Out of all the hundreds of thousands of asteroids that we've discovered so far, this was the first one to be discovered in 1801. In fact, it's the first minor planet to be discovered, so its official name is 1 Ceres. Minor planets are basically any solar system body that isn't a planet or a moon. And then this is the only asteroid to be classified as a dwarf planet, because it is the only one to be in hydrostatic equilibrium, which simply means that it's massive enough to be able to pull itself into a roughly spherical shape. So, for a very good long time, the only picture we had of Ceres was a blurry one, put together by the Hubble Space Telescope in orbit around Earth, which revealed a small ball with a very curious bright spot. And then finally, very recently, we were able to explore Ceres up close from 2015 through 2018, when the NASA spacecraft named Dawn approached and entered orbit. Dawn had used its ion engines to first explore Vesta, the third largest asteroid we know of, and then it moved on to Ceres, where it now slings around in an uncontrolled orbit for at least, say, the next 20 years or so. The spacecraft was able to shift orbits several times and get really close, at one point coming within 35 kilometers of the surface. So it is no wonder that we now have stunningly gorgeous photos of Ceres with about 1,000 times better resolution than what Hubble was able to capture. And now we have great shots of those bright spots, which can be found in the floor of Oculus crater right here. So what are those bright spots then? Well, unfortunately, they are not alien city lights, as many were hoping. After some study of the massive amount of data collected from the Dawn mission, researchers have determined that the bright material is made of sodium carbonate. In other words, washing soda or soda crystals. We already use this stuff on Earth to make glass, paper, washing detergent, and so on. It's basically salt plus limestone. And several lines of evidence point to a very recent episode of cryovolcanisms in a low-density region below this crater, pushing the material up onto the surface. And so now that bright spot in the center of the crater is named Cerealia Facula. Even better than identifying the bright spots, though, is that researchers have discovered that Ceres used to have a very significant subsurface ocean of liquid water, some of which may still be there. By now, though, most of that water is now either frozen solid or locked up in the surface crust as ice, clays, and hydrated minerals. We've even seen that Ceres occasionally emits water vapor, which is something that comets do, not asteroids. And so the line between comets and asteroids becomes a bit blurry. Ceres is only tilted at 4 degrees relative to its orbit around the Sun. So, just like our Moon and Mercury, there are areas at the poles that never see sunlight, and thus they act as cold traps for that water vapor to fall in and accumulate as water ice. This is the only dwarf planet in the inner solar system. The next one we see will be much further out, beyond the major planets. But for now, let's go get a closer look at the elephant in the room, Jupiter. Hello there, and welcome to the outer solar system. This giant planet comprises the vast majority of the planetary mass of the solar system, and it is massive enough to have the gravitational pull that can tug on the sun itself. What this means is, an observer in another star system could look this way and employ a technique called radial velocity, and they would notice our sun wobbling a little bit, and from that, they could deduce the presence of a giant planet like Jupiter. If there is one word I could use to describe Jupiter, it would be change. Things do not sit still for long on Jupiter because it is a gas giant, and it is made of the same substances as our Sun, 98% hydrogen and helium, mostly in highly compressed liquid form deep in the interior of the planet. There is no solid surface, and we now know that even its core is a giant, partially dissolved fuzzy mess. Jupiter was originally twice its current size when it first formed. Let that sink in. The largest planet in the solar system by far used to be twice its size. It has been shrinking at a very slow rate due to gravity crushing the energy out of atoms in its core. And this energy continues to stir up the atmosphere, giving rise to all of these stormy cloud belts. On top of that, this giant planet rotates stunningly quick, with one rotation every 10 hours. These cloud belts slip past each other at different speeds, fluidly mixing their gases at their boundaries. You're probably familiar with the Great Red Spot. It is a distinguishing characteristic of this planet wherever you may see it in the media. The Great Red Spot is continually changing its color every few years, with hues ranging from bright brick red to white. The surrounding cloud belts also change their colors from time to time. So sometimes the Great Red Spot can kind of blend in and look like it's disappeared, even though it's still there, churning as hard as ever. And even though it is still huge, the Great Red Spot has been shrinking a bit over the last few decades. Meanwhile, one cloud belt away from the Great Red Spot, a little bit to the south, 3 smaller white oval-shaped storms that were first seen in 1938 all merged together at the turn of the millennium, so fairly recently. That combined storm is now called Oval BA, which is about the size of Earth, and it appears to be gaining strength. So yeah, with all this change going on, it's hard to make a global, one-piece map of a gas giant. What you see here is a snapshot, and surely not what it looks like today. Okay, let's take a step back. I have to ask you, what is the brightest star in the sky? Okay, yes, the sun is, but I mean other than that, what's the brightest star in the night sky?
Sirius.
That would be Sirius, the dog star, which you can see right over there. To an observer on Earth, Jupiter sometimes appears brighter than Sirius. To me, this is one of the clearest examples of how far away, relatively dim objects like Jupiter can appear as bright as a star in the night sky. And yes, Jupiter is relatively dim. It only receives 3 to 4% of the sunlight that Earth receives, and it reflects only half of that. And yet, due to its sheer size, Jupiter still managed to reflect enough light back in the direction of Earth to make it appear to be the second brightest planet in the sky after Venus. As far as exploration goes, other than a few flybys from Pioneer and Voyager missions, and a few others not focused on Jupiter itself, there have been 2 orbiters at Jupiter. NASA's Galileo was the first craft to ever orbit Jupiter, and it arrived in 1995. And by the way, on the way here, Galileo managed to pass right by 2 tiny asteroids in the asteroid belt and take pictures of them, another first. And when it passed by one of those asteroids, named 243 Ida, Galileo discovered that even asteroids could have moons. Galileo did plenty of great science while at Jupiter, and it dropped off a small probe into Jupiter's atmosphere to take measurements. At the end of its mission in 2003, the Galileo probe itself did the same thing when it purposely veered into the cloud tops and measured extremely strong winds and high temperatures before it was vaporized. The second orbiter, which is still here today, is NASA JPL's Juno spacecraft. Now, Galileo was nuclear powered because solar panels and battery tech just weren't very good at the time. However, Juno is completely solar powered, and it is the first craft to do so out here in the outer solar system. With its mission ending sometime in 2021, Juno is swooping around the planet in large elliptical orbits so that it can periodically get close enough to study it without spending too much time inside of Jupiter's destructive radiation. So far, Juno has sent home beautiful images. It has studied the interior, discovered clusters of chaotic cyclones at the poles, determined that the magnetic field is twice as strong as originally thought. It has observed that the Great Red Spot rises 8 kilometers above the surrounding cloud tops, and more. Interestingly, the high-resolution global maps of Jupiter that we've seen so far came not from these orbiters, but from Voyager as it flew past long ago, and another from Cassini when it was on its way to Saturn. What you see here is that more recent Cassini map, plus detailed imagery of the polar regions taken by Juno. Now, let's go see what lies in wait on the other side of Jupiter.
That's very cool. Wow. Shepherd moons. There you go. amazing. Wow. That Titan? It is. It's Titan. I'm gonna pause this. I can, maybe I can't. Can't pause it, I guess. What is that? Never heard of this moon. Whoa. Wow. Is that Neptune? Oh. Wow. Uranus.
This planet has some interesting names in different parts of the world. Some of the names translate to King of the Sky, Star of Death, and Uranus. The name Uranus comes from the Greek god of the sky, Uranus, although it's more of a personification of the sky rather than a true mythological god. This is the only non-Earth planet to get its name directly from Greek mythology, instead of from some equivalent figure in Roman mythology. There simply isn't a Roman equivalent, although the literal Roman translation is Caelus, which sounds pretty cool, but it wasn't adopted because the word Caelus just means sky or the heavens, and that doesn't make sense for the name of a planet. And then I think shortly after the discovery of Uranus, the name Caelus was used for something else anyway. Even so, the name Uranus fits well given that Uranus was the father of Saturn, just as Saturn was the father of Jupiter. After being discovered by William Herschel looking through a telescope in 1781, it took about 70 years to reach a consensus on what to call it. During that time, several names were proposed, like George's Star, or Neptune George III, in honor of Great Britain's King George III at the time. But as you may guess, those names were not popular outside of Britain. Okay, enough about the name. Uranus is classified as an ice giant, which for some paints an image of a planet that is made out of solid ice or has a lot of solid ice, but that's not really what it means. Under the atmosphere, there is no solid surface to stand on, and as you go deeper inside the planet, the gases gradually turn into a liquid slush. Whereas the classic gas giants like Jupiter and Saturn are made of mostly hydrogen and helium, Uranus is mostly made of various ices, and only a small part of it is hydrogen and helium. The atmosphere that you see here is the hydrogen and helium part, but there's also some methane mixed in, which absorbs the red parts of sunlight. So what you're left with is this cyan color. We've only sent one spacecraft to Uranus, when Voyager 2 flew past it long ago in 1986. What you see here is roughly how it looked at the time. The planet can look very plain and featureless, like this, but not always, because Uranus lies on its side, so there's actually a variety of interesting features that appear at different parts of the Uranian year, and we're still trying to understand how it all works. Uranus has a thick hydrocarbon haze layer at high altitude that prevent us from seeing most of the complex cloud structures underneath, unfortunately. But as Uranus orbits the Sun, there are dramatic changes to the atmosphere that we can actually see. When Uranus is positioned like this, the poles are just sitting there facing the Sun or facing away from the Sun. Because of the long year, each pole gets around 2 years of continuous sunlight, followed by 42 years of darkness. As Uranus approaches a point 90 degrees further along in its orbit, over there somewhere, it temporarily exhibits a normal day and night cycle. And we start seeing some pretty interesting formations that make it look a lot more like its twin, Neptune. This means bright clouds, dark spots, thunderstorms poking up through the haze layers, and speedy cloud bands, all of which can now be seen by the most powerful Earth-based telescopes. And now that Uranus is entering its long summer with its other pole facing the Sun, telescopes have spotted an enormous white cap covering a large part of the planet. Uranus holds a number of mysteries, and further exploration is long overdue. In addition to the uncertainties in how the planet changes throughout the orbit, another thing we don't quite understand is why Uranus is the coldest planet in the solar system. For some reason, it just doesn't give off very much heat. So, various missions to the planet have been proposed, including one that is like the old Pioneer Venus multiprobe, which would consist of an orbiter to allow for continuous study up close, and it would drop off a handful of probes to see how things work under the planet's thick haze layers. So, fingers crossed that it gets built. Alright, see you at the next one.
You see lightning strikes hit Saturn. Wow. Oh. This is awesome. Neptune.
We've come to the last of the major planets in our solar system. Neptune has a nice blue hue, and that's very appropriate because the planet is named for the Roman god of the sea, and in practically all cultures, the name has something to do with the sea, or water, or rain. And its moons are all named after lesser sea gods and deities. In humanity's search for extrasolar planets, planets beyond our own solar system, we use the word Neptune to describe an extrasolar planet of similar mass. You might hear statements like, "We found 3 Neptunes and 2 Jupiters in this other star system," and so on. Neptune is an ice giant and twin to Uranus. There are some differences between the two, though. Neptune is heavier than Uranus. It's got more mass, more stuff in it. And so Neptune's increased gravitational compression of its atmosphere ends up making Neptune smaller than Uranus. And you can actually see high altitude clouds and cloud bands here. Neptune's blue color is more vivid, more azure than cyan. So why is Neptune more blue than Uranus? It's actually difficult to find a definitive answer for this one at this time. The two planets have fairly similar atmospheric compositions, but Neptune has a smaller percentage of methane than Uranus, so it's a bit odd that it ends up being bluer. Some claim that it's perhaps another atmospheric constituent that causes the deeper blue color. Other potential factors include things like the thinner atmosphere at Neptune, and also the planet is just warmer than Uranus. And these are all factors that could affect the color. Can you see the rings? Neptune has faint reddish rings, the outermost one having 5 distinct arcs. It's not a complete unbroken ring that goes all the way around, which is fairly unusual because generally ring material tends to spread out and complete the circle all on its own. The current best guess as to why there are arcs is because of gravity from Neptune's moon Galatea, which orbits just inside the arcs. If you look at images of the rings taken in 1989 by Voyager 2 and compare them to images captured 13 or 14 years later by a powerful Earth-based telescope, the rings appear to be decaying very quickly, and one of the arcs looks like it will disappear entirely by the end of this century. It's a powerful reminder that nothing lasts forever, not even the large-scale structures of outer space. Speaking of forever, this planet takes forever to orbit the Sun, about 164 years. It recently completed its first orbit around the Sun since it was discovered in 1846. The farther away the planet is from the parent star, not only does it have more distance to travel to go all the way around, but it also does so more slowly. Neptune is known for some other sorts of extremes. All the gaseous planets have something called differential rotation, where the different latitudes rotate at different speeds. You could easily see this happening at Jupiter, with different cloud bands appearing to move at different rates. Neptune has the most extreme differences in rotation speeds, with the polar region spinning once every 12 hours, while the wide region around the equator spins once every 18 hours. As a result, Neptune has energetic storm systems with the fastest winds in the solar system. On Earth, the highest category that we give to hurricanes is Cat 5. Here on Neptune, that same scale would have to go up to at least Cat 40 for these kinds of winds. Let's talk about the moons. As far as we know, there are 14 of them. 7 are normal, well-behaved, prograde moons that probably formed along with Neptune. The other 7 are irregular and either have wildly inclined orbits or orbit in the opposite direction, which usually means they were captured by Neptune's gravity well after its formation. The giant moon Triton is one of these, and it is very obviously captured from the Kuiper belt that lies beyond Neptune. If Triton had managed to remain out there in the Kuiper belt, it would have been considered the largest dwarf planet in our solar system, since it is a bit larger than Pluto. Because Neptune is so far from the Sun, the Sun's gravity is much weaker out here. So Neptune is able to have moons that orbit at huge distances from the planet without being stolen away by the Sun. 2 of Neptune's moons, Psamathe and Niso, have the largest orbits of any moons in the solar system, as far as we know, and they take about 25 years to complete their orbits, comparing that to Earth's moon, which takes 1 month to do the same thing. The size of that region around the body where it is able to keep things in orbit is known as the Hill sphere, and it's different for every planet. Voyager 2 is the only spacecraft that has visited Neptune back in 1989, when it completed its grand tour of the outer solar system, which is such an incredible feat and has inspired so many. As of now, there are only proposals for future missions, nothing concrete. Hopefully that changes soon. With the new space race underway, I wonder if we may see new techniques for getting to the distant planets at a quicker pace. Like, I don't know, putting a cost-effective unmanned rocket into Earth's orbit and then refilling its massive fuel tanks, letting it accelerate to great speeds and saving enough fuel to slow down for orbital insertion at the other end. I don't know. I haven't done the math on that, but I'm hopeful. Alright. We're at the last of the major planets of our solar system. So that means this is the end of the tour, right? Not so. First, let's go visit an old friend in the Kuiper belt. And then I will let you venture on to get a peek at just how big things can get in outer space.
Wow, Triton looks so amazing. It's cold out here.
Here we are at the dwarf planet Pluto, finally. Let me start by mentioning the astronomer named Percival Lowell, who started a program in 1906 to find a 9th planet. And he spent the last 10 years of his life looking for it, to no avail. Lowell's observatory later gave the job to a Clyde Tombaugh to continue this effort, and he found Pluto in 1930. Lowell was actually expecting to find a giant planet out here with 7 times the mass of Earth, but Pluto ended up being pretty tiny, so it's not exactly what he was looking for. In any case, when Pluto was found, an 11-year-old girl in England suggested it be named Pluto, and it ended up on the short list of names for Lowell's observatory to vote upon. The final choice of name was helped in part by the fact that the first 2 letters of Pluto are the initials of Percival Lowell. So now, Pluto's North Pole, right over here, has been named Lowell Regio in honor of Percival Lowell. And the heart this bright shape here, has been named after Clyde Tombaugh. And Bernie Crater, here, is named for the 11-year-old girl that proposed the name Pluto. Other features are named for famous explorers, adventurers, and even pioneering spacecraft such as Voyager, Sputnik, Venera, and so on. Many other surface features, along with Pluto's 4 moons, are named for things related to the mythological underworld. Charon is the name for Pluto's big moon. There are a lot of features on both Pluto and Charon whose names are not yet officially approved and may not ever be. For example, this dark red polar region of Charon is unofficially named Mordor from Lord of the Rings.
Nice.
But one does not simply get the International Astronomical Union to approve these names. In general, though, all of Charon's surface features are to be named after fictional things and authors and artists associated with the exploration of space. So Charon has some mountains named after Stanley Kubrick, Arthur C. Clarke, and so on. Pluto and Charon are together sometimes considered a binary planet because they orbit around a point that lies between them, called a barycenter. Same thing with the Sun and Jupiter. They effectively orbit each other around a point just outside of the Sun's surface. Also, the Pluto and Charon system is unusual among planetary systems in that both bodies are tidally locked to each other, which means that Pluto and Charon always have the same side facing the other. It would be as if only one side of the Earth could ever see the moon, and the moon just stood there forever motionless in the sky. Unfortunately, if you're standing anywhere on Charon, you'll never get to see Pluto's heart, as it is always facing away from Charon. So the way you see them moving here in tandem is how they move in reality. Now let's talk about what's happening on Pluto. As you can see, the heart has 2 distinct parts. The left side is known as Sputnik Planitia, and it is made of a slightly fluid nitrogen ice that slowly convex over time to form cell shapes. Sputnik is very, very young on geological timescales. The lack of cratering in that area, plus a study of pit formation, seems to suggest that it's younger than 300,000 years old, meaning that geological processes have erased any trace of craters that were made before that point in time. The western edge of Sputnik meets a series of chaotic and blocky mountain ranges. There are gentle winds blowing toward these mountains, and therefore form long transverse dunes that are made of methane ice. Pluto's atmosphere is hazy. It has about 20 regularly spaced haze layers that are likely created by those winds flowing over Pluto's mountains. You may have noticed that right now, Pluto is more or less directly aiming its north pole toward the Sun. What other planet can do this? Uranus. Except this time it's not a gaseous planet, but now it's one made of ice and rock. Lowell Regio up there has a yellow tinge to it. We're not exactly sure what makes it yellow, but one idea is that because this region can point toward the Sun more frequently, that additional solar radiation turns old methane deposits yellow in that area. And then, check this out over here. There are some very dark regions on Pluto, and it's such a big difference compared to the bright heart and the highlands. This particular dark reddish-brown region wraps around to the other side of Pluto, and when viewed as a whole from a distance, that region kind of looks like a whale. And it gets this color from being covered with tholins. Tholins are a tar-like substance that is formed from atmospheric nitrogen and methane being bombarded by UV rays and cosmic rays, and then it just snows down to the surface over long timescales and sticks to it. In fact, anytime you see a dark reddish surface in the solar system, it's often due to tholins. Don't know if you noticed, but as we get further away from the sun, things are getting colder and more bodies contain an abundance of water. Under all those tholins and nitrogen ice flows, Pluto's crust is made of water ice, and under that lies a liquid water ocean. And then in the center, Pluto has a big rocky core. So where are we right now? What is this place? We're in the Kuiper Belt, which is an enormous region that surrounds all the major planets of the solar system, and it contains innumerable icy bodies left over from the formation of the solar system. It is far larger than the asteroid belt that separates the inner and outer solar system. Pluto here is the largest Kuiper Belt object, or KBO, as far as we know anyway. Just as Jupiter's gravity shapes the structure of the asteroid belt, the Kuiper Belt gets its structure from Neptune. Neptune was originally closer to the Sun, but after 500 million years it suddenly started migrating outward to where it is now. It basically pushed into the original Kuiper Belt, which is how it picked up moons like Triton, and has sent a ton of other bodies into crazy orbits around the Sun, likely triggering what is known as the Late Heavy Bombardment, where every planet and moon got hit with countless objects for a long while. Those objects with crazy orbits that did not end up as craters or comets are now collectively known as scattered disk. Eris, over there, is a member of that scattered disk. After Neptune's migration, many of the remaining bodies in the Kuiper Belt were pulled into some sort of orbital resonance with Neptune, creating organized groups and gaps out here in the belt. It's very similar to how the gravity of Saturn's moons shaped the structure of Saturn's rings. Bodies in the inner ring of this Kuiper Belt now orbit twice for every 3 orbits that Neptune makes around the Sun, and these bodies are known as Plutinos. And as you may guess, Pluto is one of them. Let's talk now about how Pluto is classified. Classification helps with recognizing meaningful patterns in science, and having well-defined terms can help with communication. Think back to Ceres, the first asteroid ever discovered. When it was found, it was considered to be a planet. After all, planet means wanderer, and Ceres was a point of light wandering around against the backdrop of the night sky. 3 other large asteroids were also considered planets. But then, we started finding so many objects in that asteroid belt, just tons and tons of them. I mean, we're up to something like 750,000 now. So, at one point, it became obvious that the way we categorize these needed to be updated, and so they were all officially reclassified as asteroids. The same thing happened here with Pluto. With the discovery of Eris in 2005, it became obvious to some that the way we classify a body like Pluto needed to be updated, and so the terms planet and dwarf planet were formally defined in 2006. It was and is a very controversial decision. And of course, the way we classify solar system bodies may change once again in the future, as arguments solidify for doing things differently. For those that miss having Pluto as the 9th official planet, let me offer an upside to labeling Pluto a dwarf planet. Sure, some may have started saying there's only 8 planets, but many also started saying, and by the way, let me tell you all about Ceres, Pluto, Eris, Haumea, Makemake, and a few other very interesting bodies. So, thank you, Pluto, for sharing the limelight with your fellow dwarf planets. It is thanks to the wildly successful New Horizons flyby in 2015 that we have any kind of detail to see or talk about at Pluto. And it is sheer luck that during closest approach, it was the geologically fascinating heart side that was visible to the high-resolution cameras and sensors on the New Horizons probe. However, there's still plenty of unanswered questions and more science to be done. And for that, we would need to send another mission to Pluto. Alan Stern, the New Horizons principal investigator, has been pushing for a new mission to Pluto, one that would launch in 2030. And it would be propelled by, believe it or not, a special version of a fusion reactor made for spacecraft that is currently making good progress in the lab. It would be an orbiter that can use Charon's gravity to adjust its orbit as needed, and then afterwards it could leave to go somewhere else. And now, your journey continues. I will stay behind while you get to go out and get a good look at our sun and perhaps more. Thank you so much for doing the Titans of Space holographic tour of the solar system. And perhaps I will see you again sometime. Bye-bye.
Wow. So amazing.